Hello and welcome, fellow coders. If you have watched the tutorial up until this video, you have now reached a point where Go gets really awesome. That is because you will be finally learning the features that make Go so incredibly fast. Of course, I'm talking about concurrency. In today's video, you will learn how easy it is to run code concurrently in Go. But before we get actually into the code, we first have to understand what concurrency is. To explain what concurrency is, think about a web server that accepts HTTP requests. Each incoming request tells the server to do the following things. First, fetch data from the database. Second, retrieve other data points from a different server. Third, do some calculations on the data. And fourth, return a result back to the caller. Now imagine that every single request takes roughly 500 milliseconds to be answered. What do you think will happen if the server gets a second request within the 500 millisecond time period? Exactly, it wouldn't be able to answer the second request since it's busy answering the first one. Well, nowadays servers have many different techniques to process the second request while the first one is still being answered. But generally speaking, the ability to process multiple computations at the same time without affecting the outcome of one another is called concurrency. And that is exactly where Golang shines. You will see that Go has a super easy feature set to let your code do multiple things at the same time. If you want to create a new process that runs independently from the main process, all you need to do is to create a new Go routine. A Go routine is a function that is capable of running independently from the process starting it. So essentially, Go routines are the bread and butter of concurrency in Go. Okay, enough theory. Let's go ahead and see how Go routines look like in code. First, let me quickly run you through the code that I've prepared. Up here you see a globally defined count variable initialized with the value 0. Additionally to the count variable, we have an increment function which increments the counter by 1. Within the main function we call the increment function and print out the count variable. If I run the code, I guess it's no surprise that 1 gets printed out. So far so good. Now let's see how we can run this concurrently using Go routines. To start a new Go routine, all you need to do is to call Go before a function call. In this case, increment will run in a separate Go routine started by the main function, which is also by design of the Go language running in a Go routine. Before I explain what this code does, let's go ahead and run it. Well, we can see that the count variable does not get incremented and still has the value 0 at the time it gets printed out. But why exactly is that? As soon as the main routine hits line 12, it fires up a Go routine starting a new process that runs independently from the main process, and inside it, increment gets called. Meanwhile, the main routine runs further and prints out the value of count, which at this point in time is still 0. After that, the program stops because the main function is done running. And all of that before the Go routine, which runs in parallel to the main routine, has the chance to execute increment and set the value of count to 1. But how do you solve this problem and make sure that count gets incremented? Well, the most pragmatic way is to sleep between both function calls. This will give the increment call inside the Go routine enough time to finish executing before count gets printed out. Although this code would work just fine, finding a sleep time that is high enough so that the increment call gets executed every time and also low enough that the main routine does not get blocked too long is a pretty hard task. Let's for example wait for 100 nanoseconds and see what happens. Running the code a couple of times shows us that 100 nanoseconds in some cases is enough, in other cases it isn't. I guess I don't have to get into more detail about why this solution is not feasible. But there is a way to tell the main routine to wait until the Go routine is done executing. For that, we need a wait group instance from the sync package. What a wait group essentially does is, it groups together a set of Go routines, blocks the code and waits until every single one of them has finished executing. If you have a look at the functions a wait group has, you can see that it provides us with 3 different functions. The first one tells a wait group to wait for a specific number of Go routines. A wait group has an internal counter to keep track of how many Go routines should be running. The add function increments this internal counter by the given argument. Done tells the wait group that the execution of a Go routine has finished and decrements the internal counter by 1. The last function, wait, tells the routine that starts the wait group to wait until all started Go routines have finished their execution. So wait will block the code until the internal counter is 0. Hence, all Go routines have called done. Now let's see how this looks like in action. First, we add 1 to the wait group since we are going to start one Go routine. Second, right after starting our Go routine, we will tell our wait group to wait for it. Now, the last thing we need to do is to tell the wait group that increment has finished incrementing. One way to accomplish that would be to pass the reference of the wait group into the increment function and call the done function inside it. This is totally a viable option, but personally I don't like it. And that is for a couple of reasons. First, the function you are calling inside the Go routine shouldn't care if it is running inside a wait group or a Go routine or whatever. It should just do whatever it is supposed to. Like for instance retrieving data from its server, fetch data from a database, calculate some numbers, or in our case increment a number. But definitely definitely not deal with a wait group. The second reason is testing. Let's say you want to write a test for this increment function, even though the actual purpose of the increment function is basically as easy as it gets. Just increment one number. To test it, you would still have to create a wait group, add 1 to it, let the wait group wait just to test the incrementation of one single number, which kind of feels off. So the better way, at least in my humble opinion, is to keep the code dealing with the wait group in one single function. In our case, that would be the main function. But how do you call two functions inside a goroutine if you want them to get executed together? Well, the trick is to create an anonymous function, put the increment call as well as the done call inside it, and start the function within a goroutine. This way, all the code that has to deal with the wait group stays in one place, and your code that gets executed inside your goroutine stays clean. This feels much better, right? Now let's see what happens if I run the code. Awesome, it prints out 1 no matter how many times I run the code. In this scenario, we start only one goroutine, call increment once and wait for it to finish, and then print out the result. Easy stuff, right? But in most cases, you stop more than just one single goroutine. So let's see what happens in this case. If I, for example, create a for loop for that and let it iterate 500 times, we can put this code into it to start 500 concurrent goroutines. What will happen is that for every single iteration, one gets added to the internal wait group counter, telling it to wait for one additional goroutine, which we then start right in the next line. After the last of the 500 iteration calls is done, the internal wait group counter gets decremented to 0, telling the wait group that every single goroutine is done, the wait group stops blocking and count gets printed out. So what we expect is 500 to get printed out, right? Let's see what happens if I run the code. Well, apparently the math ain't mathing anymore. No matter how often I run the code, count is never exactly 500 like expected, but rather somewhere between 450 and 500. But why isn't it printing out 500 like it's supposed to? Well, there's a certain probability that two different goroutines which are running in parallel are trying to increment count at the same time, or more accurately, trying to manipulate the memory address of count at the same time, which causes the incrementation to only happen once. That is why the count value is never exactly 500, but close to it. And this also explains why running the code multiple times results in different values for count. You never exactly know how many goroutines are actually running in parallel and try to increment count at the same time. The technical term of what is happening right here is race condition. A race condition happens whenever two or more processes try to access the memory address at the same time, and as you might have guessed, it is a very undesirable state that you are in. So how can we make sure that the old mathematicians stop turning in their graves? We can use something like a lock to prevent simultaneous access to the memory address. And that lock is called mutex and again comes out of the sync package. Let's see what a mutex can do for us. Actually, it only has two functions, lock and unlock, which I think do not need any further explanation. So what we are going to do is, before calling increment, we use the mutex to lock access, and right after calling increment, we use the exact same mutex to unlock it again. What this does is, the mutex will make sure that everything that happens between the lock and the unlock calls will only be accessed by exactly one goroutine at a time. This way, we can make sure that our 500 goroutines which are running concurrently increment the count variable once at a time, which will bring us the expected result of 500. Thank God. Okay, now that we made sure that the count variable gets accessed by only one goroutine at a time, there is one thing that I would like to mention here. Usually, the code you're running inside a goroutine is not as simple as the increment function right here. In many cases, your code will have at least one error check, right? And if that's the case, you definitely need to make sure to unlock your mutex right here. Now imagine that you have more than just one error check in your code. The mutex must be closed in every single of these check code blocks, which is kind of tedious, right? A better way of dealing with that is to defer the unlock call right after locking the mutex. In that case, golang will take care of unlocking the mutex for you, no matter at which point of your codebase an error has been returned. Okay, what have we done today? We have seen that we first needed to introduce a wait group and second a mutex so that our goroutines acted how they are supposed to. But do we still need the wait group if the mutex takes care of locking access of the count variable? Well, let's find out. If I go ahead and comment out the wait group code, let's see what happens if I run the code. Again, the count value is not 500 at the point it gets printed out. That is because in every single iteration we start a new goroutine, 500 in total. But as soon as the 500th goroutine gets created, the for loop finishes iterating, the printLite function gets called and the main goroutine finishes. While iterating 500 times, apparently not all 500 goroutines had the time to finish. So to answer the question, yes, in this case you need a wait group and a mutex, because both of them serve very different purposes. The mutex is used to make sure that the count count variable does not get accessed by two goroutines simultaneously. The wait group on the other hand is used to make sure that the main routine waits until all 500 goroutines have finished running. Concurrency using goroutines is one of the most powerful features the Go language has to offer, and I hope that my tutorial helped you bring a little light into the shadow. So if you enjoyed watching this one, please leave a like, subscribe to the channel if you're new, and ring the bell to never miss out on any new content. Speaking of new content, in my next tutorial video we will dive even deeper into the world of concurrency, so make sure to stay tuned, and until next time, keep on coding!